Section 10.5, Producing and Consuming Messages with Spring Cloud Stream. In previous sections, you learned about the functional programming paradigm and how it fits in the Spring ecosystem, using Spring Cloud Function and Spring Cloud Stream. This last section will guide you through the implementation of producers and consumers. As you'll see, consumers are not that different from the functions you wrote in Dispatcher Service. On the other hand, producers are slightly different because, unlike functions and consumers, they are not naturally activated. I'll show you how to use them both in order service while implementing the last part of the order flow for the Polar Bookshop system. Section 10.5.1, Implementing Event Consumers and the Problem of Idempotency. The Dispatcher Service application we previously built produces messages when orders are dispatched. The order service should be notified when that happens so that it can update the order status in the database. First, open your order service project, Order Service, and add the dependencies on Spring Cloud Stream and the test binder in the build.gradle file. Remember to refresh or re-import the Gradle dependencies after the new addition.
Listing 10.17, Adding dependency for Spring Cloud Stream and test binder.
Next, we need to model the event we'd like order service to listen to. Create a new com.polarbookshop.orderservice.order.event package and add an order dispatched message class to hold the identifier for a dispatched order.
Listing 10.18, a DTO representing the event about orders being dispatched.
Now we'll implement the business logic using a functional approach. Create an order functions class, com.polarbookshop.orderservice.order.event package, and implement a function to consume the messages produced by the Dispatcher Service application when an order is dispatched. The function will be a consumer responsible for listening to the incoming messages and updating the database entities accordingly. Consumer objects are functions with input but no output. To keep the function clean and readable, we'll move the processing of order dispatched message objects to the order service class, which we'll implement in a minute.
Listing 10.19, Consuming messages from RabbitMQ.
Order service is a reactive application, so the dispatch order function will consume messages as a reactive stream, a flux of order dispatched message. Reactive streams are activated only if there's a subscriber interested in receiving the data. For that reason, it's critical that we end the reactive stream by subscribing to it, or else no data will ever be processed. In previous examples, the subscription part was handled transparently by the framework, for example, when using reactive streams to return data via a REST endpoint or to send data to a backing service. In this case, we have to explicitly do that with the subscribe clause. Next, let's implement the consume order dispatched message event method in the order service class to update the status in the database for an existing order after it's dispatched.
Listing 10.20, Implementing the logic for updating an order as dispatched.
Consumers are triggered by a message arriving in the queue. RabbitMQ provides an at least one delivered guarantee, so you need to be aware of possible duplicates. The code we implemented updates the status of the specific order to be dispatched, an operation that can be executed several times with the same result. Since the operation is idempotent, the code is resilient to duplicates. A further optimization would be to check for the status and skip the update operation if it's already dispatched. Finally, we need to configure Spring Cloud Stream in the application.yml file so that the dispatch order in zero binding, inferred from the dispatch order function name, is mapped to the order dispatched exchange in RabbitMQ. Also, remember to define dispatch order as the function that Spring Cloud Function should manage, and the integration with RabbitMQ.
Listing 10.21, Configuring Cloud Stream bindings and RabbitMQ integration.
As you can see, it works the same way as the functions in Dispatcher Service. The consumers in Order Service will be part of the Order Service consumer group, and Spring Cloud Stream will define a message channel between them and an order dispatched.order service queue in RabbitMQ. Next, we'll complete the order flow by defining a supplier responsible for triggering the whole procedure. Section 10.5.2, Implementing Event Producers and the Problem of Atomicity. Suppliers are message sources. They produce messages when an event happens. In Order Service, a supplier should notify the interested parties, in this case Dispatcher Service, whenever an order has been accepted. Unlike functions and consumers, suppliers need to be activated. They act only upon invocation. Spring Cloud Stream provides a few ways to define suppliers and cover different scenarios. In our case, the event source is not a message broker, but a REST endpoint. When a user sends a post request to order service for purchasing a book, we want to publish an event signaling whether the order has been accepted. Let's start by modeling that event as a DTO. It will be the same as the order accepted message record we used in dispatcher service. Add the record to the com.polarbookshop.orderservice.order.event package in your order service project, order service.
Listing 10.22, a DTO representing the event about orders being accepted.
We can bridge the REST layer with the stream part of the application using a stream bridge object that allows us to send data to a specific destination imperatively. Let's break this new functionality down. First, we can implement a method that accepts an order object as input, verifies it's accepted, builds an order accepted message object, and sends it to a RabbitMQ destination using StreamBridge. Open the order service class, auto-wire a StreamBridge object, and define a new publish order accepted event method.
Listing 10.23, implementing the logic for publishing events to a destination.
Since the data source is a REST endpoint, there is no supplier bean we can register with Spring Cloud function, and therefore there is no trigger for the framework to create the necessary bindings with RabbitMQ. Yet, in listing 10.23, StreamBridge is used to send data to an accept order out 0 binding. Where does it come from? There is no accept order function. At startup time, Spring Cloud Stream will notice that StreamBridge wants to publish messages via an accept order out 0 binding, and it will create one automatically. Similar to the bindings created from functions, we can configure the destination name in RabbitMQ. Open the application.yml file and configure the binding as follows.
Listing 10.24, configuring CloudStream output binding.
All that's left now is calling the method whenever a submitted order is accepted. That's a critical point, and one of the aspects characterizing the Saga pattern, a popular alternative to distributed transactions in microservice architectures. To ensure consistency in your system, persisting an order in the database and sending a message about it must be done atomically. Either both operations succeed, or they both must fail. A simple yet effective way to ensure atomicity is by wrapping the two operations in a local transaction. To do that, we can rely on the built-in Spring Transaction Management functionality. Note: the Saga pattern is described extensively in Chapter 4 of Chris Richardson's book, Microservices Patterns. See this link. I recommend you check it out if you're interested in designing business transactions that span multiple applications. In the order service class, modify the submit order method to call the publish order accepted event method and annotate it with transactional.
Listing 10.25, defining a Saga transaction with database and event broker.
Spring Boot comes pre-configured with transaction management functionality and can handle transactional operations involving relational databases, as you learned in Chapter 5. However, the channel established with RabbitMQ for the message producer is not transactional by default. To make the event publishing operation join the existing transaction, we need to enable RabbitMQ's transactional support for the message producer in the application.yml file.
Listing 10.26, configuring the output binding to be transactional.
Now you can write new integration tests for the supplier and the consumer, like we did for the functions in dispatcher service. I'll leave the auto tests to you, since you have the necessary tools now. If you need inspiration, check out the source code accompanying this book, Chapter 10/10end/order service. You will also need to import the configuration for the test binder, import test channel binder configuration.class, in the existing order service application test class to make it work. We've had a nice journey through event-driven models, functions, and messaging systems. Before wrapping up, let's look at the order flow in action. First, start RabbitMQ, PostgreSQL, Docker Compose up-d polar RabbitMQ polar Postgres, and dispatcher service, /Gradle W boot run. Then run catalog service and order service, /Gradle W boot run, or from Docker Compose after building the images first. Once all those services are up and running, add a new book to the catalog.
See this code.
Then order 3 copies of that book.
See this code.
If you order a book that exists, the order will be accepted, and order service will publish an order accepted event message. Dispatcher service, subscribed to that same event, will process the order and publish an order dispatched event message. Order service will be notified and update the order status in the database. Tip: you can follow the message flow by checking the application logs from order service and dispatcher service. Now the moment of the truth. Fetch the order from order service.
See this code.
The status should be dispatched.
See this code.
And it is. Great job. When you're done testing the system, stop all the applications, Control-C, and Docker containers, Docker Compose down. That concludes the main implementation of the business logic for the Polar Bookshop system. The next chapter will cover security for cloud-native applications using Spring Security, OAuth 2.1, and OpenID Connect. Polar Labs. Feel free to apply what you've learned in the previous chapters and prepare the dispatcher service application for deployment. 1. Add Spring Cloud Config client to dispatcher service to make it fetch configuration data from config service. 2. Configure the cloud-native build packs integration, containerize the application, and define the commit stage of the deployment pipeline. 3. Write the deployment and service manifests for deploying dispatcher service to a Kubernetes cluster. 4. Configure Tilt to automate the dispatcher service's deployment to your local Kubernetes cluster initialized with Minikube. Then update the Docker Compose specification and the Kubernetes manifest to configure the RabbitMQ integration for order service. You can refer to the Chapter 10/10n folder in the code repository accompanying the book to check on the final result. See this link. Deploy the backing services from the manifests, available in the Chapter 10/10end/polar deployment/Kubernetes/platform/development folder with kubectl apply F services.